Okay, so let's begin today with the homework for AC analysis. There's there's two of them. First one is fundamentals about sinusoids, and then the next one after that is performing circuit analysis for AC sources. So let's bring up the class notebook. Oh, no, that's not it. Let's see. Okay. And 201. How many of you have already submitted this homework? Okay, any questions? How many of you are still, not still, how many of you are working on it or have yet to begin working on it? Okay, let's get those questions. 16, but I wanted to see if anyone had any questions about 15. 15 was day before yesterday, Monday. Okay, all right, well, let's go to 16 then. AC analysis phasers. Several students have sent me emails about, about the course, and they were trying to understand where they are in the course, and they were afraid of like falling behind, not being able to catch up. So I'm going to respond via an announcement so that it addresses several issues all at once. So again, I'll post an announcement sometime later today, perhaps in the evening, to provide a bit more clarification. Okay. All right. So homework 16. When is it due? Made it due November 5th. It's due today. How many of you already? Okay, so I think a couple of students said they already submitted this, and there are some students who are beginning to work on this. Okay. All right, 519, 520, 21, 23, 27, and 28. So let's begin with 19. 19 is the steps for adding or subtracting two or more sinusoidal waveforms. So the steps are pretty straightforward. This is something that I go over in the lecture videos. And the first thing we do is we need to ensure that we convert from the time domain into the frequency domain, meaning express the sinusoidal waveform as a phasor. Phasor is a vector representation, so it has magnitude and the phase angle. We can directly write the phasor from the amplitude or the magnitude given in the time domain expression. So if it's V of t, we take Vm and then the phase angle in degrees and directly write down the phasor from that information. Okay. So here are just the steps listed. This is kind of self-guided, but if anyone has any questions, I'd be happy to clarify. Okay. What must be true of sinusoids in order for them to be added or subtracted? Anyone know the answer to this? It's a fundamental question. So if we wish to add or subtract two or more sinusoidal waveforms, then their frequencies must be the same. If the frequencies are different, they cannot be added or subtracted. They will remain as two separate quantities. Okay, so the answer is the frequencies must be the same. The phase angles do not matter. The height, the amplitude, or the magnitude does not matter. Okay, when we add or subtract, we are adding or subtracting the magnitude and or the phase angle. Okay, but the frequencies must be the same. If the frequencies are not the same, they cannot be added or subtracted. Right? Yes. The first one. Okay. All right. I'll go to that part A, but does everybody understand part B? Okay. All right. In part A, what steps do we follow in adding sinusoidal currents or voltages? So everybody take a look at the steps. What did we say? We first need to convert it into vector form, meaning we write the phasor, right? So let's look at the first item. Determine the phasor for each term. Yes or no? Yes. Then do we multiply the phasors? Anyone? No. So that's a no. Add the phasors? Well, the answer is in the question itself. What steps do we follow in adding sinusoidal currents or voltages? So that's a yes. Another one, convert the product to polar form. Yes or no? No, because there's no product because we're not multiplying. Convert the sum to polar form. Yes or no? Actually, that should be a no because the sum is the result of the addition, meaning the terms are already in polar form. Okay, so sometimes, actually, you know what? I might end up confusing myself. Might have to look at the answer. The sum could be in algebraic or in polar form because modern calculators can do so nowadays. So I want to say that should be a yes. Okay, that should be a yes. And then after that is convert the product to algebraic form. There's no product, so there shouldn't be conversion of product to the algebraic form. Second to last is convert the sum to algebraic form. And I want to say that should be a no. And then lastly is the write the corresponding sinusoidal time function. So that should be a yes. But again, sometimes this is I wouldn't say it's a trick question. It's just that the system just takes the question and the answers literally. Okay, so let's just go to the solution view and see if I'm right. Okay, yeah. So determine the phasor for each term, yes. And we add the phasors, that's correct. Convert the product to polar form, no. Convert the sum to polar form, yes. And then finally write the corresponding sinusoidal time function. Okay, so 4 of those steps. Now, these 4 steps are not in order. Actually, let's see. Determine the phasor for each term, add the phasors, convert the sum to polar form. Okay, they are in order. They are in order. Some of the questions in these homework assignments, they have the multiple choice and they are out of order. It will ask you to list it in order. Okay, so in this case, these are completely in order. And then part B, of course, we already spoke about. All the sinusoid must have the same frequency. So that's question 1. If you're not logged in, I suggest you log in so you can solve it and finish your homework as we go along. Okay, all good? All right, 519 or 520, sorry. Describe 2 methods to determine the phase relationship between 2 sinusoids of the same frequency. So read the statements and let me know what you think the answer is for the first one. There are two statements on there. The first is the phasor diagram. Second one is the sinusoidal waveform. So the vector, the phasor is a vector. The vector rotates clockwise or counterclockwise. Anyone remember? Or if you have not yet watched the lecture videos, you might have seen me make that diagram in class. Which way is the vector rotating? Think about the quadrants, the 4 quadrants on a graph. Which way do the numbers go? So the answer to this is counterclockwise. So examine the phasor diagram and consider it to rotate counterclockwise. If phasor A points in a given direction before phasor B by an angle theta, we say that A, the two options are either leads B or lags B. The answer, of course, it's right there in the statement. If phasor A points in a given direction before phasor A, the word itself suggests that it leads. Absolutely. So A leads B by angle theta, or that B, this of course would mean that it lags. These kind of questions are not going to be on the final, by the way. These are to reinforce fundamentals for students while they are learning. Okay. All right. How about the second one? Examine plots of the sinusoidal waveforms versus time. If A reaches a point by an interval delta t before B reaches the corresponding point, we say that A, again, the same thing. The keyword is before. And so if it's before, then the answer is obvious. We just spoke about it. Say that angle A blank B by the angle theta equals what? And there's two options: pi delta t over t or delta t over t into 360 degrees. You're performing a conversion. Yes. Yes. That is correct. Here, let's request the answer. Ah. There you go. Okay, next question. 521. Suppose we are given two sinusoidal waveforms, voltage V1 of t and voltage V2. Voltage V1 is 100 cos omega t, V2 is 100 sine omega t, and we must reduce it to a single term. What do you think is the answer? It's only asked for the vector notation. It's not asking for the sine wave. It's not asking Vm of t or Vs. So it's not asking for Vs of t. It's simply asking Vm with an angle of theta. Okay. So what's the first thing we check? Absolutely, we check the frequency, whether the frequency is the same or not. If the frequencies are not the same, we can't add them. In this case, the frequencies are same. They're both omega. The next thing to do is to check whether we are all in cosine form or not. If they are in cosine form, then we can write the phasor directly. So 100 cos omega t becomes 100 with an angle of 0, and 100 sine omega t must be converted to cosine. What is the relationship from sine to cosine? How much? Sine x is equal to cos of x minus 90. So we subtract 90 degrees. And so 100 sine omega t becomes 100 cos omega t minus 90 degrees. And so the first waveform is 100 angle 0. The second waveform is 100 angle minus 90. Okay. And now we perform the math. Okay. So on your calculators, my calculator is from the 90s. It's not programmable, so I cannot perform um, mathematical operations directly. So I cannot program an equation in there and it would not be able to give me a direct answer. So I have to convert. We convert from polar to rectangular form and rectangular to polar form, Cartesian and polar coordinates, which are basically in the complex plane. It's the same thing, the three sides of a triangle. Okay. To perform this math, again, you need to be an expert at utilizing your own devices. So simply plug in the values and it'll spit out one single answer. But you need to learn how to do this on your own devices, right? But just to give a little bit of ground knowledge. In the complex plane, we have the real axis and the imaginary axis. By the way, when we say real and imaginary, imaginary is just a term. It doesn't mean it doesn't exist. There is a basis for using it. Okay, let's just think of them. I like to think of them as just notations. This was a hard concept for me to grasp when I was a student. Like if it's imaginary, then how are we using it? But it's not really imaginary. Okay, so we have the real and the imaginary axis, and we have right. That's a little bit better. Position could be all right, let's just say it's symmetrical. So when a vector starts, we have this vector here that represents the phasor. This has a length of Vm with an angle of theta. Theta is this angle right here. Okay. This length is Vm, and this is also there in the lecture notes. I just like to do this. So this is fundamental. This is fundamental math concepts. If you take this vector and project the extension of this vector on the x and y axes, we obtain the Cartesian or the rectangular coordinates. Okay. Actually, that's not a vector. All right. The projection on both axes gives us So this is, let's just call it A. Let's call this B. So when we convert from rectangular to polar and polar to rectangular, that is what we're doing. It's the three sides of a right angle triangle. Okay, it's the three sides of a right angle triangle. So this is known as the polar form. Rectangular coordinates. So Vm theta is A plus or minus JB, the real portion plus the imaginary portion. Okay, and then vice versa. When you are in polar form, multiplying or dividing is straightforward or easy. And when you're in rectangular form, addition and subtraction is easy. Okay. So for instance, if you're trying to add V1 plus V2, they're both in polar coordinates or polar form. Your calculators can perform this math. My calculator cannot. And so what I do is I convert it into rectangular coordinates, which again is the way we used to do things before we had calculators, right? That's how engineers and scientists used to do things. And so convert to polar, polar to rectangular. Actually, I wrote it out the wrong way. To be more accurate, that's the magnitude of the vector, that's the phase angle. So when you multiply two complex numbers, what happens to the magnitudes? The magnitudes can be multiplied, and the phase angles are added together. When you're dividing two numbers together, anyone remember this from complex number math? Or has it been a long while, perhaps? The two magnitudes get divided, and the phase angles are subtracted. Numerator minus the denominator. Okay. Even though we have powerful calculators at our fingertips, it still behooves us as engineers to know how to do this. Okay. And then if you have rectangular coordinates or rectangular form for complex numbers, it's straightforward. A plus or minus JB, you add or subtract with another number, C plus or minus JD. The real portion gets added or subtracted together, and the imaginary portion gets added or subtracted together. Okay. So that's why all of that conversion takes place. So in the book assumes that not everyone has the calculator, so it shows you the basic steps. And that's why in the homework problems, it asks you to list all these steps, like convert from polar to rectangular, rectangular to polar. Does that make sense to everyone? Okay, but now again, as I said, if you have powerful calculators, you can perform any math, any mathematical operation, addition, subtraction, multiplication, division in any form. You could add a number in polar coordinates with a number in rectangular coordinates, and your calculator should be able to do that. Okay. And again, it's imperative that every student learns how to do this. There are online resources. People have been doing this for a long time. People also have the same calculator models for a long time. There are peers in your class that have the same models. You can go through the discussion forum and just search for one that has the same model, reach out to them. Okay. All right, let's take a pause. Let me know if you have any questions. And then we'll go back to the homework. How many of you finished lab 6? How was it? Confusing? All right, let's do the homework and then I'll explain a little bit. And how many of you have lab 6 coming up? Just one? Lab 6 is by far actually the shortest lab. You build the circuit, you take the measurements, and you create it on GeoGebra, and you're done. Did y'all use GeoGebra? Okay. Yeah. You did it manually? Wow. Why? Why? Who is your instructor? None on. Okay. I mean, there's value to do. It's not. I'm not discounting that. There is value in learning how to do that. Okay. But was it expressly prohibited to use GeoGebra or online websites? Oh, okay. Okay. There is value in that, so I am not going to discount that or argue against that. But GeoGebra, it just makes things very easy. Yes. Yes. Let's go back to the homework. 5 point, which one? This one? Okay, let's see. View all hidden parts. Draw the phasor diagram showing V1, V2, and Vs. State the phase relationships between each pair of these phasors. Okay. I don't have the answers with me. So what is the answer for V1? If any student performed this on your calculator, what answer did you obtain? Well, actually, V1 is given, so we don't need to do anything. It's 100 cos omega t. So it's a vector that has an angle of 0 degrees. So it's lying flat on the x-axis, positive real axis, with a length of 100. Okay, with a length of 100. So if I was to do, let's see, V1, starting point here, and then angle is 0. Start point should be 0. End point on x should be 100. Why is it's only going up to 10? Oh, because it's okay. Gotcha. I need to convert it into rectangular coordinates. So angle 0, start point x00, 0, end point x. Why is it? That's interesting. Minus 10. Okay, let's see that 1. And then V2 is, what was V2? 100 with the angle of minus 90. So start point is 0. Angle is minus 90. Or 270. Okay. And then VS, what's the answer for VS? Okay, all right. So then we just enter the coordinates. Was that your question? I mean, is this what you're looking for? Okay. You can go to the solution view and just see how it's plotted out. Yep, there it is, V1, V2, and VS. One thing I'd like to point out, which is something also point out in the lecture video, is that if both vectors are the same, right, and the angle is just divided by 90, then the summation or the sum would be exactly in the center. So you have one vector at 0, the other one has like 90 or minus 90. Then the angle for the sum would be at 45 or minus 45. And we can see that here. VS is at minus 45. So in this case, I think it's coming up as minus 8.1. Start point, 0.1, minus 8.1, 8.3, and then 7.5 and 7.6. I guess it's multiplied by a factor of 10. Not really sure. Did anyone get this incorrect when they entered? What are you obtaining at your end? Uh-huh. So if you try to enter 141, what does it do? Yes, but there is an angle that we inputted. So if you go to the standard view, I'm gonna enter, and if I say V1, enter the point, then I have the angle. Angle is going to be 0. This needs to be 0. This needs to be 0 to start off. So we're starting off at 0, 0. And then endpoint should be at 100, but it only allows me to go up to 10, which I assume is like a multiplied by a factor of 10. And then V2, that's V1, and add V2, and V2 should go from 0 to minus 90. Instead of minus 90, it asks me to input as 270, which is the same thing. So 270, and then my endpoint should be minus 100, but it only goes up to minus 10. So that's that. And VS should be angle of, let's see, minus 45 is 270. Sorry, what? 315. 315. 270 plus 45. Yeah, 315. Start point would be at 0, 0. End point should be at, let's see, it's minus 141, right? It's 141. So end point should be at, I need to convert it into X and Y coordinates. So if we add this, I can't do it without the math. Someone perform the math conversion and convert it into rectangular coordinates, please. 141 with an angle of minus 45. Which one? No, because it's the hypotenuse of a right angle triangle. Minus 10 and 10? Seriously? X is 10 and this is minus 10 and it works. I mean, the length is different. Oh, yeah. Brain fart. Sorry. Yeah, that is correct. I'm thinking in terms of the length of the vector, but the XY coordinates, of course, is the length of the X axis and the Y axis. Sides of a right angle triangle. I'm thinking in terms of the length of the vector, which is 141. As I said, brain fart. But yes, that is the answer. Yeah. Let's submit this. Hey, I got it correct. Thank you. Does that answer your question? Yeah. Okay. What is the phase relationship between V2 and V1? Which one is ahead? Which one is lagging? Well, it says V2 lags V1 by 90 degrees. Absolutely. The negative sign is implied by the lags. If it was positive 90, it would be leads. Phase relationship between Vs and V1. That one's easy or straightforward. Phase relationship between Vs and V2. Again, that one's straightforward. So shouldn't have any issues. All good on this question? Okay, let's move on to the next one. Reduce 5 cos omega t plus 75, cos omega t minus 95 or 75, and 4 sine omega t to the form of Vm cos omega t plus theta. In this case, we are adding and subtracting sinusoidal waveforms, and we have to write the time domain expression, meaning we have to perform the inverse phasor transform at the end. Okay, we must perform the inverse phasor transform, which, I mean, it sounds like a mouthful, but all we are doing is we are taking the vector, we're taking the magnitude and the angle, and simply applying the inverse phasor transform by writing Vm cos omega t plus or minus theta. Okay, so again, similar to the previous one. V1, current I1 of t has an RMS value, leads by V1t, current and voltage of the same frequency, and then asks you to show the phasor. So that's, yeah, straightforward, which is the correct expression for I1 of t. RMS value needs to be converted to a peak value. So RMS times √2 would give you IM. And that's about it. The last one, again, is the same as the previous one. Only difference is phase angles are different. Okay. So you choose the answers and you enter it on there. There is, let's see, filters, transfer functions. Okay. And finally, power. Okay. Any other questions about the homework? Yeah. You want more? I mean, I can design more. 20 homework is plenty in a 10-week quarter. Let me explain lab 6, okay? So we have inductors and capacitors, right? Inductors are made out of coils of wire. Wire, what's the resistance of a wire? Ideal wire. All right, so we got this ideal wire, R is 0. If you take this wire and you loop it around, what should be its resistance? Anyone? Still 0. So an ideal inductor has a resistance of 0. A real life inductor does not. Okay, so if you take two parallel plates and you put them together and separate it by a certain distance or an insulating material, then the resistance should be infinite. Okay, should be infinity. However, no real life insulator has infinite resistance. There's always some finite number that we can put on it. Could be mega ohms, could be tera ohms, could be whatever. But there is always a finite resistance. Okay. So capacitors are not ideal. I mean, real life components, neither inductor, neither capacitors are ideal, right? So real life inductors are modeled real life inductors have resistance and they're modeled as a inductor in series with a resistor. Okay. You have to understand this. It's the same spiral coil. If you measure the inductance between those two terminals, you will measure some inductance